As we showed on Monday's plenary presentations, 1Spatial technology enables location master data management. It allows you to use automated rules to do several things. Those things include measuring and improving data quality, preparing and migrating data to a different system, synchronizing data to propagate updates between systems, or to infer and generate new data. And this applies both for internally data within an organization, but also when matching data between organizations to cross-reference it or link it to an authoritative source. And from that, we can start to build some semantic meaning between the data sets and infer new information. The OneIntegrate rules engine is complemented by the One Data Gateway portal. This provides controlled access to authorized users to run the rules in an easy-to-use portal for uploading the data to be processed. One Data Gateway can be used for a number of data automation use cases, so that could be data validation, data improvement and enhancement, such as propagating and linking to multiple networks, or it could be data acceptance and ingest of supply chain data. Over the last year, 1Spatial technology has been driving forward, and I'll talk about some of the developments here. For OneIntegrate, our rules engine, we've been expanding the range of data access formats. So for example, we can access Google BigQuery data, read and write to it. Access directly to Esri feature services. We're adding access to web feature services, and that includes accessing the OS data hub. And also true 3D data, being able to read it, validate it, process it, and write it back out. And in parallel, we're expanding data operations in the product. So for example, integrating with machine learning libraries, and we'll see some examples of those later. And generally expanding the capability and power of the rules engine. One Data Gateway has seen some major releases, which includes access to any sort of rules that we want to run as defined in OneIntegrate. Powerful user and organization management to control who accesses what and when. And also identity and single sign-on, so integrating with third-party identity management systems. We've added dashboards and analytics and access to that data so that it can be processed either within Data Gateway or in third-party analytics software. And reports on your upload that can be downloaded as a PDF. And also custom branding so that you can color it and brand it so that the site can look with the look and feel that you need for your solution. And then 1Spatial LMAP, which is the application platform for building mobile solutions. These can be running on Android or iOS, and they allow the creation of simple targeted applications. And these have got lots of power and capability because they have the power of the rules engine within them. So you can view, search, edit data, but importantly run rules as you're editing on your mobile device. So examples of applications that we've built for customers are incident management applications or network update applications. This is a location master data management architecture using this approach. Here there's a central enterprise store of data, but it could be one of many sources, each of which masters a different aspect of the same real-world assets. At the top, Data Gateway is providing cloud access to rules-based apps, such as supply chain data ingest, leakage prediction using machine learning to predict leakage risk, positional accuracy improvement to improve the location of assets based on reference data, or automatic generation of traffic management plans. We'll see some examples of those in a moment. These apps allow cloud-based access to the capabilities which depend upon or sometimes even augment the core enterprise data. At the same time, there's integration with external systems, and these might be data services which we access on demand in order to provide reference data. So for the Data Gateway apps, for example, Ordnance Survey Data Hub. These external systems might also be running rules via the APIs or accessing the core data or the dashboard and statistics for analytics insights. So the application of rules can give us all sorts of benefits in terms of automation. Here are some examples of the use of rules on utility network data or in utility use cases. Now, some of these will show a proper demo of these later on in Tom's presentation. So one example is traffic management plan generation, automating the process of when anyone needs to dig up the road, they need to submit the plan of the road signs and the traffic lights to the local authority, and that's usually a manual process using CAD tools, takes a long time. This is showing how to automatically generate the plans from the surrounding data, from the topography and the street network information. Another example is positional accuracy improvement. And this is where the pipes or the networks or the cables are in the wrong position, either because they've been captured against a base mapping data that's since been updated, or simply it's through historic migration and import of data. And now there's some more accurate information that can give us a positional offset so that the network is in the correct position. And that could be from a real world survey. It could be I've got a capture of the manhole covers and I can associate those with positions on my network and update the network. Or it could be the base map shifted and we're going to do a shift in sympathy. That's a good example of where rules can be used to automatically update and improve that data. Another example is missing connector inference. So where we have examples in the UK where networks were inherited from the local authority to the water companies, and the sewer information about the connectors, so from the main sewer up to the customer's house, that information wasn't available. So it could be inferred automatically using rules to get a much clearer picture of what's out there in reality. And that saved huge amounts of surveying to get a quick idea of roughly where the network would be and what its length would be. Another example is automatic generation of schematics from network data. That's an example of where rules can be applied to data to generate something new, generate a simplified view of the network that can then be put onto a PDF or a piece of paper or layers in a GIS to help the engineers and the designers and the planners work with the data. One example, and this is again something that Tom's going to demonstrate later in his session, is leakage detection via machine learning. Up to now we've been talking about rules, and these rules typically are explicit rules that are designed by a data expert. They know what needs to happen, they know the process, and they know the outcome. But with machine learning, that's a parallel approach, where you don't tell it how to do the task, you just give it examples of, here are the inputs, this is the output I require. And the machine learning algorithms will work out themselves how to match that, how to create the patterns. But it's very important when doing that the data that's fed in is clean and correct and unbiased. Otherwise, all we're doing is training a network to do the wrong thing. So we use rules to help clean up the data to feed it into a machine learning process. And also, what we need to feed into a machine learning process is essentially numbers, the information encoded into a set of statistics. And so we use the rules as well to extract that information from spatial and non-spatial data. So for example, information about each asset, what's its length, what's it near, what sort of road does it go underneath, and how busy is that road? All that information we can use rules to extract and pass into the machine learning libraries. And at 1Spatial, we're integrating machine learning libraries with our products. So things like TensorFlow from Google or Keras, and those being integrated into our standard products to complement the rules library approach. The automation that we've talked about in this past is now extended to include support for true 3D data in OneIntegrate. And that means that the current use cases for 2D data still apply now for 2D and 3D data. So use cases of validating data to measure data quality, cleaning data to improve its quality, integrating data from different sources, or inferring new information. A whole range of data formats are supported for this, and this means that it enables whole new use cases for the data. So for example, that could be underground construction, checking for clashes, for containment. It could be environmental purposes, use cases for building energy efficiency based on their size and their shape and their location. We've also seen use cases around taxation, looking for line of sight to certain things, looking for the sizes of the apartments within a block and checking they're paying a consistent tax rate. As well as 3D capability in 1Integrate, there's also the real-world 4D product from 1Spatial. This allows a view of the assets as they are in the real world. So this combines 3D data, 2D data, and any imagery such as LiDAR scans, or here we've got photo textured surfaces that have been captured out in the field. And this allows us, for example, to view the 2D data as it is in the GIS, compare that to the 3D images, and see a first-person view, but also an orbital view that's going to combine imagery from subsurface and above ground. And this can save huge amounts of time before going out in the field. It can be inspected to check what are the assets down there, what is the condition, what equipment do I need to bring with me before I go down and perform maintenance tasks. Now there's one industry trend which is also having an impact, but this again is something for which the rules and automation can greatly help, and that's a move to the utility network model that Esri has developed. And this is something they're trying to get all of their utilities customers onto so that they can fully benefit from connectivity and topology and other parts of the network capabilities in the stack. And what that means is utilities have to now concentrate on how do they migrate their systems and their data into this utility network model. And that migration process is something that we've been doing for a long time with all sorts of different models and technologies and systems using rules. And the 1Spatial approach applies very well here. So clean and prepare the data, migrate the data in, and then keep it maintained and synchronized with other parts of the system. So we've seen a number of examples of 1Spatial technology, but what people are actually trying to achieve with this software are things like the ability to have digital twins. Now the concept of digital twins, people have talked about them a lot for several years now. When I first heard the concept of digital twin, it was described as a digital representation of a real world asset, and I thought, well, we've had that for years. We've had GIS tools and databases and CAD tools, but the digital twin concept is it's not just a record of the asset as it was when it was installed, because that's what a GIS or an asset management system is if you don't keep it updated with the latest information. So for example, if we're doing network tracing based on a pipe's diameter and depth and slope, if it's gravity fed for example, then we will be tracing the network as it was when it was clean and installed. But over time that would have degraded, the pipe would have been clogged, it would have been sagged, the height might have changed, the condition would have changed, the surrounding information would have changed. And so digital twin is about keeping that information up to date, and typically that means using sensors or some sort of measurements to record that near real-time property of the asset, which means that the network tracing and the analysis can be much more accurate. It can represent how the asset's actually performing now. And that's a key part of location master data management, is synchronizing that information and so ensuring the network is clean and the information that relates to it is kept up to date and synchronized. I've talked about digital twins and some other technologies, and there are many of these buzzwords casually thrown about these days. Everyone feels they need to be on some bandwagon, but in reality none of these is a silver bullet that solves all problems. They're simply tools or approaches or ways of thinking to add to the toolkit and use in the right way. And by using them in the right way, then we can transform what we do and how we work. The common theme with all of these is automation, and there's certainly more of that happening. So if we look at digital twins, machine learning, sensors, smart meters, they're all about automation and automation of the data. Now, automation doesn't mean replacing people. We'll use tools and technology at work, and whether that's emails, video calls, spreadsheets, cloud storage for sharing, they're all marketed as productivity tools, but we're just as busy at work, we're no less busy. It's just that we've been achieving more in the same time. People often say, what did we do before emails? But the answer was slightly less. We knew less about what was happening and shared less information. Now that overload is not necessarily always a good thing, but imagine how slow projects would be if we did the same number of things at the same speed without all of these tools. So this productivity increase is always happening slowly and steadily. Now, one example of automation is self-driving cars. A few years ago, great strides were taken and moved these from impossible to theoretically possible to actually in use. But they are only in use in the most straightforward cases. Initially, they've been rolled out on wide US highways in good weather. And the other use cases become exponentially harder. What about country lanes, ad hoc signs and detours? There's a tractor coming towards us blocking the road. And these more complex use cases will take much longer to achieve. So these essentially are more like the driver aids than full automation, and full automation will take a long time to achieve. So fully autonomous driving for all vehicles in all conditions still seems a long way off. But if we look at the utilities industry, then there's already large amounts of automation, and many of the more easily reachable Californian freeway type automation has already been achieved or even being exceeded. We have SCADA systems of sensors and intelligent networks, and that's all possible and happening. And we've seen some examples today, and Tom will show more later, of powerful next level automation using rules that go beyond just scripting. And as this automation grows, then not only are the next step of harder problems getting solved within a single network, but we're also going to see more network connectivity between different networks to help create connected grids and smart cities. And with more machine communication to deliver not just automation of repetitive manual tasks, but also drive insights and provide support for human decision making. Now, maybe this will never be fully automatic. Maybe there's always going to be a driver in the car, or always going to be a network engineer making decisions about shut-off. But automation with decision support can free people up to focus on the interesting and the harder problems. The point is that automation is powerful, and that after the initial quick wins, the problems do get harder and require more intelligent systems and more effective data to achieve them and unlock the true potential.
Thank you, Seb. A brilliant presentation showcasing some of our tech and highlighting the importance of accurate data consumption into systems, and what your perspective is on digital twins. That was brilliant. Let's now take this opportunity to answer some questions. So, first one for you, Seb. I've always worried that real-world models create false confidence in data for users. How would you manage this?
Yeah, so that's sort of a classic question, actually, and some of it goes back to what Paul was talking about accuracy versus precision. And there's a risk that by being very confident and describing something to 7 decimal places, that sounds like we've got very deep insight, which we may not have. And so typically, and this is sort of, I guess, a standard scientific approach, is these things should be a hypothesis. I think this is how the real world works. And then you measure, you compare that against the real world, and you see what the differences are, and you check those things. So if we are hypothesizing that, or we've simulated and we think that a BMX rider will get quicker if they're heavier, as Paul said, the next thing you do is you try it. Now, it's not always easy to try it. So it's not, we might always have a BMX bike and a rider to try it on in our equivalent world. Yeah. But it's comparing reality against what you've simulated, and making sure that there's enough confirmation of what's happened, and then continually revisiting that model, revisiting the real world data to say, well, can we spot where the differences are, or even is there a problem, or is there something we can improve in how we capture data because we've identified something that's missing, which is affecting the simulation.
Brilliant. Thank you. Very detailed answer there, Seb. Oh, another one. Based on your email example, could too much data be a bad thing? So I know there are, in utilities companies and other companies alike, it's that problem of having so much data, you don't know what to do with it. What do you have to say about that, Seb?
Yeah. I was using the email example. At the time, I was thinking people hate emails. Maybe this isn't a great example, but So it's absolutely true. And the more data you capture, that doesn't mean you're going to be more insightful or be able to do things better unless you use that data very well. And that's, that's where we see automation being key. So if we go to the examples of emails, I know that behind the scenes, there's various bits of software in my IT department, and even our internet service providers are filtering out loads of spam that never even gets to me. So that level of automation is key. So that's automating things. And I have fairly good confidence in that. Actually, good questions. I've got fairly good confidence in that because I can have a look through the things they have tracked now and then and say, actually, yeah, that's doing a good job. But even then, there's still emails that come through, and I then will unsubscribe them because I guarantee I never agreed for you to send me an email, but you've sort of been playing fast and loose with GDPR and managed to send me an email. So I'll unsubscribe that. So there's sort of certain levels of discipline of keeping things clean. But unless there is, if we go to the point of data, unless there are automation approaches to deal with that data, either it's going to cause huge to make use of it, and then you lose the benefits, or it's just overwhelming and people are just going to, well, I'm going to go on a hunch rather than the data. So absolutely, you can get buried in the amount of data unless you have some automation to help filter it out. But from the previous question, we have to keep going through, making sure that automation is getting us the right results. We don't just trust it right from the beginning.
Absolutely. Great answer. Okay, I think we've sort of answered some of those automation questions in there. That was brilliant, Seb. But let's go on to this one here. So can 1Spatial's LMDM solution be continually improved or added to, adapted to changes or demands on my network? So how adaptable is that?
Yeah, I mean, that's a key thing that we've seen from implementations of software, throughout the years, for both software we use or we see our customers using, and that's the flexibility, because people spend huge amounts of effort and money in installing software, deploying it, and then within years or even sometimes months, the situation changes, the needs change. So it needs to be very flexible to keep up with that, and that just needs to be something that needs to be taken on board and designed from the beginning. So for example, from 1Spatial point of view, the rules and the approaches we do are all configurable using a user interface, and that means the data experts can evolve them and keep them up to date. And it doesn't rely on building a piece of software. We're too scared to touch it because it requires a 6-month development cycle to update it and redeploy it. So that flexibility is key to keep up to date. Otherwise, it just becomes a legacy system that you then have to worry about.
Yeah, absolutely. Okay, this follows really well into another question that I'm going to propose regarding the utility network model. So how do you think things like Esri's utility network model will change the way data is managed for utilities?
So the intention behind the utility network model was to try and get some consistency across all the utility providers to allow them to unlock some of the benefits that otherwise are just out of reach. So network tracing or data simplification or hiding the complexity. So for example, let's take an example. Say we've got a substation, electricity substation. At a high level view of the network, that is just a thing that connects some cables. But if you look inside it, there's all sorts of complexity in there. And different people will want that view or not, depending on the level they're looking at the data. And so some of that benefits in terms of having higher and low levels of detail in is something that's really valuable, but a lot of organizations can't unlock it because their data's not yet in that rich way. So by moving to the utility network model, there's that overhead of I need to migrate my data, I need to understand, make sure my systems are working with it. But once it's there, then there are lots of benefits that can be unlocked that otherwise we're always just out of reach or a bit too difficult. We'll do that in a couple of years' time. We'll worry about that later. And that should make once it's been migrated to, it should accelerate some of those more advanced techniques.
Brilliant. And we know that's all surrounding, the importance of high data quality as well, and making sure that the data is up to a certain standard, and that standard is, it's general across all the utilities. So kind of on that point, do you think things like 3D, AR and VR present an increased risk if the data is incorrect, because we aren't quite at that point where the data is all at a good standard. We've got quite a long way to go still.
Yeah, absolutely. There is, and this partly goes to the human perception problem of, if you're seeing something in an AR model, you're seeing it simulated in the real world. It seems so realistic that there's a false sense of security that's where it is. So, for example, I might be looking at the ground and it's showing me the underground pipes before I dig. There is reality to that can give a false sense of security, and people have already been talking about, well, what's the best way to represent that? So maybe when we draw these things under the ground, they should be drawn in a sort of blurred out way, so that it implies that, well, this is just an approximation. It's as much a psychology problem as a technical one, and I don't think anyone has yet a very strong approach to how to avoid that uncertainty of things in AR give you a false sense of confidence. Other than, okay, you can make sure the data is correct. Well, that'd be a great answer, but it's how to tell people if it's uncertain, how to communicate that.
Brilliant. Thank you so much, Seb. That was fantastic. Really great chat there.